Lieutenant Colonel Creighton Abrams commands the 37th Tank Battalion, an element within General George Patton's 4th Armored Division. His unit occupies defensive positions across the agricultural flatlands of Lorraine, a region that has witnessed armored warfare since the division broke out from Normandy hedgerows in early August. Morning fog reduces visibility to approximately 200 meters. Intelligence officers from the 12th Corps' headquarters have transmitted urgent warnings throughout the night. German armored formations are concentrating for a major counteroffensive. Reconnaissance reports estimate at least 200 tanks, predominantly Panther medium tanks from 5th Panzer Army units recently transferred from the Eastern Front. Abrams surveys his battalion's ammunition status. Standard procedure requires detailed inventory before anticipated combat. His Sherman tanks carry a mixed load of 76mm rounds, high explosive shells for engaging infantry and soft targets, white phosphorus for marking and obscuration, and armor-piercing projectiles for defeating enemy armor. Among these conventional rounds, his crews have received a small allocation of experimental ammunition marked T4 HVAP, high-velocity armor-piercing, Tungsten core, experimental designation. Battalion supply officers issued exactly 4 rounds per tank 3 weeks earlier, accompanied by written orders emphasizing conservation. Use sparingly. Critical shortage nationwide. The tactical mathematics confronting Abrams are straightforward and discouraging. American tank doctrine since 1940 has divided armored warfare into 2 distinct missions. Medium tanks like the M4 Sherman provide mobile fire support for infantry divisions, engaging enemy personnel, fortifications, and light vehicles with high explosive shells. Specialized tank destroyer battalions, equipped with thinly armored but heavily armed vehicles mounting 3-inch guns, handle enemy armor threats. This division of labor worked adequately during North African campaigns against German Panzer III and Panzer IV tanks. It has proven catastrophically inadequate against the Panther. The M62 armor-piercing projectile standard ammunition for 76mm guns since production began in 1943 can penetrate 109mm of vertical steel armor at 1,000 meters range. The Panther's frontal glacis plate measures 80mm thick, but angles at 55 degrees from vertical. This slope increases effective thickness to approximately 140mm. Basic ballistics equations confirm what frontline crews have learned through bitter experience. M62 ammunition cannot defeat Panther frontal armor at combat ranges. Deflection is not a possibility, but a certainty. What Abrams cannot know as he prepares his battalion for the coming engagement is that over the next 11 days, his outnumbered force will destroy 86 German tanks while losing 25. Sherman's a kill ratio that contradicts every pre-war prediction about German Panther encounters. This outcome depends entirely on those 4 experimental tungsten rounds per tank, ammunition that nearly every expert in the ordnance department declare impossible to manufacture. If you appreciate detailed, evidence-based World War II history, please like this video and subscribe to the channel. Leave a comment telling us where you're watching from. We love hearing from our international audience. To understand why American tank crews faced such desperate circumstances in September 1944, we must examine the fundamental armor mismatch between American and German medium tanks. The M4 Sherman entered production in February 1942. Initial variants mounted a 75mm M3 gun, adequate for defeating contemporary German armor. The tank's design prioritized reliability, ease of manufacture, and strategic mobility over maximum armor protection or firepower. Frontal hull armor measured 51mm at 56 degrees slope on early models, providing effective protection against German 50mm anti-tank guns. The Sherman's mechanical reliability critical for operations across North African deserts and later European mud came from its commercial truck-derived powertrain and relatively simple suspension system. German designers approached medium tank development from different premises. The Panther, designated Panzerkampfwagen V, entered production in January 1943 as a direct response to Soviet T-34 encounters on the Eastern Front. German engineers studied captured T-34 tanks throughout 1942, analyzing their sloped armor schemes and powerful 76mm guns. The Panther incorporated these lessons while adding German manufacturing precision and superior optics. The Panther's frontal glacis plate 80mm at 55 degrees created effective protection exceeding 140mm against kinetic penetrators. Side armor measured 40 to 50mm, adequate against most American tank guns at typical engagement ranges. The tank's 75mm KWK-42L7O gun-fired armor-piercing projectiles at 935 meters per second muzzle velocity, capable of penetrating Sherman frontal armor at ranges exceeding 2,000 meters. American ordnance officers recognized this disparity by mid-1943. The Ordnance Department initiated development of the T-26 heavy tank, later designated M26 Pershing. This 46-ton vehicle mounted a 90mm gun capable of defeating Panther armor at standard combat ranges. However, production delays, shipping priorities, and doctrinal debates about heavy tank necessity meant Pershing tanks would not reach European theater of operations in significant numbers until March 1945. Frontline crews developed improvised tactics to compensate for equipment limitations. Standard operating procedures emphasized flanking maneuvers, requiring numerical superiority and favorable terrain. Tank commanders aimed for track wheels and suspension systems, hoping to immobilize Panthers for artillery engagement. Some crews attempted ramming attacks, using the Sherman's superior maneuverability at close range to position German tanks for vulnerability. Casualty rates reflected the desperation of these methods. By July 1944, Sherman crews in Normandy reported consistent defeats in frontal engagements with Panthers. After action reports from 1st Army tank battalions documented cases where M62 armor-piercing rounds deflected off Panther frontal armor at ranges under 100 meters. Tank destroyer battalions, supposedly equipped to handle heavy armor threats, discovered their 3-inch M62 ammunition performed marginally better, but still could not reliably penetrate Panther frontal protection at combat ranges. The mathematical problem was straightforward. The M62 armor-piercing projectile achieved approximately 792 meters per second muzzle velocity from 76mm guns. At 1,000 meters, this velocity decreased to approximately 670 meters per second due to atmospheric drag. The kinetic energy available for armor penetration, calculated from projectile mass and velocity, proved insufficient against highly sloped, hardened steel plate. Penetration mechanics follow the Demar formula, which accounts for projectile diameter, velocity, mass, and target obliquity. Even optimistic calculations confirmed M62 ammunition could not defeat Panther glacis armor at ranges where German tanks could engage effectively. 3rd Army Headquarters received increasingly urgent requests for improved ammunition throughout August 1944. Tank battalion commanders submitted formal reports documenting ammunition inadequacy. Crew morale reports noted declining confidence in equipment. General Patton personally contacted Ordnance Department leadership, demanding immediate solutions. The answer was already in development, but its path from laboratory to battlefield had been blocked by bureaucratic resistance and material scarcity. The solution to the Sherman Panther problem originated not in high-level strategic planning, but in technical research conducted at Aberdeen Proving Ground, Maryland. The Ballistics Research Laboratory at Aberdeen functioned as the Army's primary facility for ammunition development, testing, and analysis. Civilian engineers and military ordnance officers collaborated on improving existing weapons and developing new technologies. In early 1943, one civilian engineer whose name appears in declassified documents only as BRL research staff due to wartime security classifications, began investigating alternative approaches to armor penetration. His background included pre-war work on industrial cutting tools and familiarity with German technical literature. Unlike many career ordnance officers focused on incremental improvements to existing designs, this engineer examined fundamental penetration mechanics. He studied pre-war German research on subcaliber penetrators. German engineers had published papers in the mid-1930s describing projectiles where a small, dense core traveled inside a larger diameter carrier that fell away after firing. The concept offered theoretical advantages. By reducing projectile mass while maintaining propellant charge, designers could achieve significantly higher velocities. Higher velocity meant greater kinetic energy delivery to the target, potentially compensating for reduced projectile size. The engineer obtained technical specifications for tungsten carbide, an industrial material used primarily in cutting tools and dies. Tungsten carbide forms when tungsten powder combines with carbon at temperatures exceeding 1400 degrees Celsius, creating an extremely hard ceramic metallic compound. On the Mohs hardness scale, tungsten carbide measures approximately 9.0, compared to hardened steel armor at approximately 6.5. This hardness differential suggested tungsten projectiles might retain structural integrity during armor penetration where steel projectiles deformed. He drafted preliminary calculations in January 1943. A standard M62 76mm armor-piercing projectile weighed approximately 15 pounds and achieved 792 meters per second muzzle velocity. If engineers could reduce projectile weight to approximately 9 pounds while maintaining the same propellant charge, theoretical muzzle velocity would increase to over 1,000 meters per second, a 30% improvement. If the penetrator core weighed only 3 pounds of tungsten carbide, enclosed in a lightweight aluminum carrier, velocities might exceed 1050 meters per second. These calculations assumed conventional propellant charges and standard gun tube strength. The concept required no exotic explosives or metallurgy beyond tungsten carbide production, already an established industrial process. The engineer designed a preliminary configuration, a 38mm diameter tungsten carbide core, approximately 12 centimeters long, wrapped in an aluminum body to match 76mm bore diameter. The aluminum sabot would separate after leaving the barrel, allowing the dense tungsten core to continue downrange. He submitted his preliminary analysis to the Ordnance Department's Ammunition Review Board in February 1943. The response documented in meeting minutes was unanimously negative. 3 primary objections dominated discussions. First, tungsten supply limitations. The United States produced approximately 4,400 tons of tungsten annually in 1943, according to War Production Board records. Industrial demand consumed most of this output. Tungsten-hardened steel used in armor plate production, cutting tools essential for machining tank components, and electrical contacts in various military systems. Ordnance officers calculated that diverting tungsten to ammunition production would reduce availability for these critical applications. The trade-offs appeared unacceptable. Second, manufacturing complexity. Tungsten carbide's extreme hardness made machining difficult. Cutting tools required diamond or carbide edges. Tight dimensional tolerances necessary for ballistic accuracy demanded precision grinding operations. Mass production seemed implausible given existing manufacturing capacity already stressed by conventional ammunition demand. Third, weapon system stress. The proposed ammunition would generate chamber pressures and bore stresses exceeding design specifications for 76mm guns. Artillery officers with decades of experience maintained that operating at maximum pressure limits invited catastrophic failures in combat conditions. The proposal violated established safety margins. The review board filed the engineer's report with a notation: concept theoretically interesting but practically infeasible for field deployment. Development focus remained on the T-26 heavy tank program and improved conventional ammunition designs. The civilian engineer, however, did not abandon his work. Aberdeen Proving Ground maintained extensive test facilities for ammunition development. Standard procedure required formal authorization for test firing, but small-scale research projects operated under more flexible guidelines. The civilian engineer secured informal permission to conduct exploratory materials testing using surplus components and rejected production samples. He obtained tungsten carbide blanks from civilian cutting tool manufacturers. These were production rejects, components that failed quality control standards for industrial applications, but remained suitable for experimental use. The engineer machined these blanks on borrowed lathes, working outside normal duty hours to avoid drawing attention from ordnance officers who might terminate unauthorized projects. For sabot components, he cannibalized 57mm anti-tank rounds from early war stocks. These rounds used aluminum components that could be modified to fit 76mm dimensions. The engineer fabricated steel base plugs and windshields from raw stock, matching designs to standard 76mm ammunition specifications where possible. His first functional prototype, assembled in March 1943, looked crude compared to production ammunition. The tungsten core showed visible machining marks. The aluminum sabot fit loosely in some dimensions, requiring shims for proper centering. The overall round met basic safety requirements, but would never pass conventional quality control inspection. March 15, 1943. First test firing occurred at Range 8, a facility normally used for experimental propellant testing. The engineer mounted a standard 76mm M1A1 on a fixed test stand, allowing precise measurement of barrel stress and chamber pressure. He installed a chronograph, a device measuring projectile velocity by timing the shadow cast as the round passed between two light sensors at 50 feet downrange. The engineer loaded his improvised round and fired from behind a reinforced observation position. The weapon discharged with noticeably different sound characteristics than conventional ammunition, sharper crack rather than the booming report of standard 76mm fire. Chronograph readings showed 1043 meters per second muzzle velocity, exceeding his calculations by approximately 4%. This suggested efficient propellant combustion and minimal bore friction from the smaller tungsten core. The aluminum sabot separated cleanly 50 feet downrange, exactly as designed. The tungsten core continued toward a target plate, captured German face-hardened armor steel, 80mm thick, angled at 55 degrees to simulate Panther glacis configuration. This plate had stopped every previous test of M62 conventional ammunition. The tungsten core penetrated completely, creating a neat hole approximately 40mm in diameter. No deformation of the core was visible. The penetrator continued through the steel plate, defeated a second backing plate, positioned to catch fragmentation, and buried itself in the earthen backstop. The engineer examined the target plate carefully. The hole showed characteristics distinct from conventional armor-piercing impacts. Steel armor penetrated by conventional rounds, typically displayed pedaling radial cracks extending from the impact point where metal yielded under stress. The tungsten penetration showed minimal pedaling, suggesting the tungsten core, as superior hardness, had sheared through steel rather than forcing it aside through plastic deformation. He repeated the tests 6 times over the following week, achieving consistent results. Chamber pressure measurements, recorded by piezoelectric sensors installed in the gun chamber, averaged 45,000 pounds per square inch, well within the M1. A 1 gun's rated maximum safe pressure of 50,000 psi. Barrel inspection after test firing revealed normal rifling wear, actually less than standard ammunition due to the tungsten core's smaller bearing surface. The engineer compiled test data into a comprehensive report, including high-speed photography showing sabot separation, chronograph velocity measurements, chamber pressure graphs, and photographs of penetrated armor plates. He submitted this report through proper channels to the Ordnance Committee in late March 1943. The committee's response, documented in official correspondence dated April 2nd, was severe. The test methodology described generates chamber pressures at the maximum limit of weapon safety specifications. Your chronograph readings suggest velocities that exceed approved operating parameters for the M1A1 gun system. Continued testing along these lines is not authorized. Recommend immediate cessation of this research direction. The committee chairman's covering memorandum noted that operating weapons at maximum design limits left no safety margin for combat variables. Extreme temperatures, ammunition stored in adverse conditions, worn gun barrels, or propellant variations. The marginal safety factor made the concept too dangerous for field deployment, regardless of performance advantages. The civilian engineer prepared a detailed rebuttal. His pressure measurements came from calibrated sensors, not estimates. The velocity readings were verified across multiple tests. Barrel wear analysis, conducted by Aberdeen's metallurgy department, showed no stress fractures or excessive erosion. He requested permission to conduct extended duration testing, 100 rounds through a single gun barrel, to verify wear characteristics under sustained use. The Ordnance Committee did not respond to this follow-up submission. The reports were classified and filed. Development focus remained on conventional ammunition improvements and the T-26 heavy tank program. What the committee failed to anticipate was that someone outside the standard review process was paying attention to technical reports from Aberdeen. Major General Gladian Marcus Barnes commanded the Research and Development Service within the Ordnance Department. A 1912 West Point graduate, Barnes had served in artillery positions during World War I before transitioning to ordnance development roles during the interwar period. Unlike many senior officers whose technical knowledge ended with their academy education, Barnes maintained active interest in engineering developments and regularly reviewed technical reports from Aberdeen and other testing facilities. The civilian engineer's reports reached Barnes's desk through routine distribution of all ballistics research summaries. Barnes read the actual test data rather than relying on committee summary recommendations. He reviewed high-speed photography showing clean sabot separation and tungsten core flight characteristics. He examined pressure curves and noted the sustained consistency across multiple test firings. Most importantly, he studied photographs of penetrated armor plates that had stopped every conventional 76mm projectile tested. Barnes requested the complete test film footage from Aberdeen. After reviewing the materials, he contacted the Ballistics Research Laboratory directly and spoke with the civilian engineer who conducted the testing. Barnes's questions focused on practical deployment concerns. Could the design be simplified for mass production? What tungsten quantities would be required for meaningful field deployment? Could existing manufacturing facilities produce the ammunition, or would new production lines be necessary? The engineer provided detailed responses. The design could be standardized using conventional ammunition manufacturing techniques with minor modifications. Tungsten requirements per round amounted to approximately 1.4 kilograms, significant, but not prohibitive if production volumes remained moderate. Several civilian contractors already possessed tungsten carbide production capacity from cutting tool manufacturing. Barnes made a command decision. He authorized production of 500 test rounds for field evaluation, bypassing the standard Ordnance Committee review process. This authorization came directly from his office as Chief of Research and Development, technically within his authority, but highly irregular given the committee's previous rejection. The directive arrived at Aberdeen Proving Ground in mid-May 1943. Produce 500 rounds of T4 HVAP ammunition to standardized specifications for field testing in North Africa Theater. Priority classification: urgent. Funding authorized from R&D discretionary budget. The civilian engineer and his small team worked continuously through May and June. They established relationships with F.H. Sterling Steel Company and Union Carbide Corporation, both of which agreed to supply tungsten carbide cores from excess industrial capacity. The Frankfurt Arsenal in Philadelphia, Pennsylvania, produced aluminum sabot components using modified tooling from 37mm APCR, armor-piercing composite rigid ammunition production, a similar sub-caliber design used in limited quantities during North African campaigns. By late June 1943, Aberdeen had assembled 547 completed rounds, meeting basic specifications. Quality control inspections revealed some dimensional variations in tungsten core production, but all rounds met minimum safety standards for test firing. General Barnes arranged shipping to North African Theater, specifically to ordnance testing units attached to 5th Army in Tunisia. The Ordnance Committee learned of this production run only after ammunition was already in transit. Committee Chairman Colonel James Thompson submitted a formal protest memorandum to Barnes's office, noting that the decision circumvented established review procedures and committed scarce tungsten resources to an untested concept. The memorandum concluded, should this ammunition prove unsafe or ineffective in field conditions, responsibility lies entirely with the authorizing officer. Barnes acknowledged the memorandum without modifying his orders. The ammunition would be tested in combat conditions. Results would determine future production decisions. American forces in North Africa encountered limited numbers of German Panther tanks during the final phases of the Tunisia campaign in May 1943. Most German armored forces in Africa fielded Panzer III and Panzer IV models, which conventional 76mm ammunition could engage effectively. However, ordnance testing units recognized that future European operations would involve heavier German armor. The 500 T4 HVAP rounds arrived in Tunisia in July 1943, shortly after the campaign concluded. Ordnance officers established testing protocols using captured German tanks and armor plates. Initial tests focused on safety verification. Would the ammunition function reliably in field conditions? Would chamber pressures remain within safe limits when ammunition was exposed to desert heat? Test crews fired approximately 100 rounds through various 76mm guns, including weapons with significant barrel wear from combat use. No catastrophic failures occurred. Chamber pressures measured consistently at 44,000 to 46,000 pounds per square inch, confirming Aberdeen's laboratory results. Barrels showed no unusual stress after firing sequences. Penetration testing occurred at a range facility near Tunis using captured Panther frontal armor plates. Standard M62 armor-piercing ammunition fired from 500 meters range achieved no penetrations against Panther glacis armor at 55-degree slope. 20 rounds tested, 20 deflections. T4 HVAP ammunition from identical range and angle, 18 penetrations in 20 attempts. The 2 failures to penetrate resulted from rounds striking at extreme edge angles where core mass proved insufficient, not from fundamental design flaws. Testing Officer Major Robert Patterson submitted his report to Ordnance Department headquarters in August 1943. T4 HVAP ammunition performs as specified. Penetration capability exceeds conventional AP ammunition by significant margin. Recommend immediate production authorization for European theater deployment. The Ordnance Committee convened in late August to review Patterson's report and Barnes's authorization for initial production. Debate centered on tungsten availability and production capacity rather than technical effectiveness, which field tests had demonstrated. War Production Board records from 1943 showed United States tungsten production at 4,400 tons annually. Industrial consumption analysis indicated approximately 4,200 tons committed to existing war production, 2,100 tons for armor plate hardening, 1,400 tons for cutting tools and industrial machinery, 700 tons for electrical contacts, specialty alloys, and other military applications. This left approximately 200 tons potentially available for ammunition production. Each VAP round required 1.4 kilograms of tungsten carbide. Converting this to production capacity, 200 tons equals 200,000 kilograms, divided by 1.4 kilograms per round, yields approximately 143,000 rounds, assuming complete diversion of available tungsten to ammunition, which would impact other critical production programs. The Ordnance Committee authorized limited production, 10,000 rounds monthly beginning October 1943, with distribution prioritized to tank destroyer battalions and select tank battalions equipped with 76mm guns. This production rate required approximately 14 tons of tungsten monthly, a manageable diversion from total supply. However, ammunition did not reach frontline units in significant quantities until mid-1944. Production delays resulted from multiple factors: establishing manufacturing relationships with civilian contractors, quality control challenges in tungsten carbide core production, integration of VAP production into existing ammunition plant schedules already operating at maximum capacity, and shipping priorities that favored conventional ammunition in limited cargo space. By D-Day, June 6, 1944, the Ordnance Department had produced approximately 47,000 HVAP rounds. None were allocated to assault units landing in Normandy. Strategic planners, influenced by pre-war doctrine emphasizing infantry support over tank versus tank combat, determined that standard high-explosive ammunition should comprise the majority of embarked ammunition loads. Tank crews went ashore with minimal anti-armor capability against Panthers. American tank battalions encountered Panthers in significant numbers beginning in mid-June 1944. German armored reserves, held back during the initial invasion, counterattacked against expanding Allied beachheads. Panzer Lehr Division, equipped with Panthers and Panzer IV, engaged elements of 1st Army near Creighton. The 2nd SS Panzer Division deployed Panthers against British forces east of Caen. Combat reports from these engagements documented severe ammunition inadequacy. Captain Murray Franks, commanding Company F 2nd Battalion, 66th Armored Regiment, filed a representative after-action report on June 18th. Engaged 2 Panther tanks at approximately 800 yards range. Crew fired 6 rounds M62 AP ammunition. Observed 5 definite hits on frontal armor. No penetrations achieved. Enemy vehicles returned fire, destroying 1 M4 tank and damaging another. Company withdrew under smoke cover. Similar reports accumulated throughout June and July. Tank crews developed improvised tactics, emphasizing close-range engagement, flanking maneuvers when terrain permitted, and combined arms cooperation with infantry and artillery. These tactics reduced but did not eliminate the fundamental problem. Sherman tanks could not reliably defeat Panthers in frontal engagement at typical combat ranges. The first HVAP ammunition reached Normandy in late July 1944. Initial allocation provided 2 rounds per 76mm gun, insufficient for sustained combat, but adequate for testing operational effectiveness. Ordnance officers established battlefield testing protocols using captured Panther tanks as targets. Testing occurred at a captured German tank depot near St. Lay on August 3rd. A 76mm gun crew engaged a Panther tank hull from 400 meters. M62 ammunition, no penetration, visible denting of glacis plate. HVAP ammunition, complete penetration, exit hole visible on rear hull plate. The demonstration convinced tactical commanders of HVAP's effectiveness. General Omar Bradley, commanding 1st Army, requested immediate increase in HVAP allocation. Ordnance Department authorized 4 rounds per 76mm gun for units engaged in Operation Cobra, the breakout offensive from Normandy beginning July 25th. This modest allocation reflected continued tungsten scarcity and production limitations. August proved critical for American armored operations. Third Army, activated under General Patton on August 1st, began rapid advances across Brittany and toward the Seine River. German forces attempted to counterattack at Mortain, committing significant armor reserves including multiple Panther battalions. American tank crews, now equipped with limited HVAP supplies, achieved improved kill ratios compared to earlier engagements. Staff Sergeant William Buckmarsh, gunner in an M4A3 Sherman from 4th Armored Division, recorded his experience in a letter written August 15th. "We finally got ammunition that works against Panthers. 4 rounds per tank. Orders are to use them only when you have a clean shot. We save the regular AP for Panzer IV and other targets. When a Panther shows up, we maneuver for position, then use 1 HVAP round. Usually that's enough. The difference is incredible. Rounds that used to bounce off now punch right through." Operational analysis from August 1944 showed measurable improvement in American tank survival rates once HVAP ammunition became available. 7th Armored Division reported a 23% reduction in tank losses during the Falaise pocket operations compared to June-July period, attributing much of this improvement to FVAP effectiveness against German armor. However, supply remained critically limited. The Ordnance Department increased production to 15,000 rounds monthly in August, but demand from multiple armies vastly exceeded supply. Distribution priorities favored units in heavy contact with German armor, creating shortages elsewhere. American tank crews developed unofficial methods to supplement their HVAP allocation. This is where the account of scavenging Soviet tungsten cores from battlefield wrecks originates, though documentation is limited. Red Army forces did use a PCR ammunition in their 57mm and 76mm anti-tank guns, employing similar tungsten carbide core technology. Some American units operating in regions previously contested by Soviet forces may have recovered these munitions. However, declassified logistics records indicate most HVAP ammunition came through official supply channels, not battlefield improvisation. The mythology of widespread tungsten scavenging appears exaggerated in post-war accounts, though isolated instances probably occurred. By September 1944, 3rd Army was advancing rapidly into Lorraine, outrunning supply lines. Ammunition stocks of all types ran low. HVAP allocation remained at 4 rounds per tank, the same limited supply that would determine outcomes at Arracourt. 3rd Army's advance into Lorraine created an exposed salient. By mid-September, the 12th Corps occupied positions east of Nancy, with 4th Armored Division holding the northern flank near Arracourt. German commanders recognized this as a strategic vulnerability. Field Marshal Walter Model, commanding Army Group B, concentrated 5th Panzer Army for a major counteroffensive. The operational plan called for 3 armored divisions, 11th Panzer Division, 113th Panzer Brigade, and 111th Panzer Brigade, to attack the 12th Corps' positions, sever supply lines, and recapture the Marne-Rhine Canal crossings. Intelligence staffs estimated German attack force at approximately 260 tanks and assault guns, including 165 Panthers. 4th Armored Division, commanded by Major General John Wood, deployed 3 combat commands across a 30-mile front. Combat Command A, which included Abrams's 37th Tank Battalion, held positions at Arracourt. The division's operational strength on September 18th totaled 177 medium tanks, 104 M4 Shermans with 75mm guns, 73 M4A1 and M4A3 Shermans with 76mm guns. Only the 76mm variants carried HVAP ammunition 4 rounds per tank, 292 rounds total across the division. September 19th dawned with dense fog reducing visibility to less than 300 meters. This favored American defensive positions allowing closer engagement ranges where numerical superiority mattered less. German forces attacked in company-strength formations, approximately 12 to 15 tanks per assault group. The 37th Tank Battalion occupied hull-down positions along ridgelines south of Arracourt. Tank commanders had established interlocking fields of fire covering likely approach routes. Standard defensive doctrine called for allowing enemy forces to close to medium range 600 to 800 meters before engaging. Lieutenant Colonel Abrams issued specific instructions regarding HVAP use. Hold EVAP rounds for Panthers only. Engage Panzer IVs and assault guns with standard AP. Do not waste tungsten rounds on suppressive fire. Every EVAP shot must be a deliberate, aimed engagement with high probability of penetration. The 1st German Assault Group approached from the northeast at approximately 0630 hours. Fog concealed American positions until Panthers closed to within 700 meters. Abrams's lead company engaged with M62 conventional ammunition first, following standard procedure to range targets and force German tanks to button up close hatches and rely on vision ports, reducing situational awareness. Several M62 rounds struck Panther frontal armor, creating visible impacts but no penetrations. The Panthers returned fire, their 75mm KWK-42 guns capable of defeating Sherman armor at current range. One Sherman took a penetrating hit through the turret. Catastrophic ammunition explosion killed the crew instantly. Abrams ordered HVAP engagement. His gunner loaded one of the 4 precious tungsten rounds. The Panther, approximately 600 meters distant, presented a clear frontal aspect ideal conditions for tungsten penetrator performance. The gunner aligned crosshairs on the center mass of the Panther's glacis plate and fired. The VAP round struck with characteristically sharp impact, distinct from the cracking boom of standard ammunition hitting armor. Tungsten carbide core penetrated the glacis plate and continued through the fighting compartment, striking ammunition storage near the driver's position. The Panther exploded violently, turrets separating from hull as stored rounds detonated. Abrams's company engaged 7 more Panthers over the next 20 minutes, firing 8 HVAP rounds total. 7 Panthers were destroyed outright, 1 damaged and abandoned by its crew. No HVAP rounds failed to penetrate when striking frontal armor at angles less than 60 degrees. This pattern repeated across 4th Armored Division's front throughout September 19th and 20th. American tank crews used HVAP ammunition sparingly but effectively, achieving extraordinarily high first-round hit rates because commanders reserved tungsten rounds for situations with high probability of success. German after-action reports reflect confusion about American ammunition capabilities. The 111th Panzer Brigade's War Diary entry for September 20th states, "Enemy anti-tank weapons demonstrate unexpected effectiveness against frontal armor. Multiple Panthers destroyed by frontal penetrations at ranges previously considered safe." Cause unknown. The Battle of Arracourt continued through September 29th as German forces launched repeated attacks against 4th Armored Division positions. Each assault followed similar patterns. German armor advanced in company or battalion strength. American defenders engaged at medium range with conventional ammunition before switching to HVAP for killing blows. Detailed analysis of the battle comes from multiple sources. 4th Armored Division after-action reports, the 12th Corps intelligence summaries, captured German unit war diaries, and post-war historical studies conducted by the Army Historical Division. These documents provide comprehensive picture of the engagement. Total American losses: 25 M4 Sherman tanks destroyed, 41 damaged but recovered and repaired. Approximately 120 casualties killed and wounded. Total German losses: 86 tanks destroyed, confirmed by battlefield recovery and analysis. 114 additional tanks damaged beyond field repair capability. Approximately 395 casualties. The kill ratio 3.44 to 1 in favor of American forces contradicted all pre-war expectations about Sherman Panther engagements. Analysis of destroyed German vehicles showed that approximately 68 Panthers were knocked out by frontal armor penetration, suggesting HVAP ammunition as primary cause. The remaining Panthers fell to flank shots, mechanical breakdown in combat, or abandonment after crew casualties. American HVAP expenditure during the battle. 4th Armored Division fired approximately 214 HVAP rounds over 11 days of combat. This represents an average of 2.93 rounds per 76 mm gun, less than the 4-round initial allocation, because crews conserved ammunition carefully and some tanks were lost before expending full loads. Hit probability for HVAP ammunition at Arracourt. Approximately 74% of HVAP rounds fired resulted in confirmed tank kills. This remarkable figure reflects the doctrine of holding tungsten rounds for high-probability shots, rather than using them for suppressive fire or long-range speculation. Weather conditions heavily influenced the battle. Fog and rain limited visibility throughout most of the engagement, reducing average combat ranges to 400 to 800 meters. This favored American defenders who knew the terrain and could position for close-range ambush. German Panthers' long-range advantage, their ability to kill Shermans at 2,000+ meters, became irrelevant when visibility seldom exceeded 600 meters. Tactical innovation by American commanders proved crucial. Rather than passive defense, 4th Armored Division conducted aggressive local counterattacks when German formations became disorganized. Mobile reserves moved rapidly between threatened sectors, concentrating force against isolated German penetrations. This aggressive defense prevented German forces from achieving the breakthrough necessary for operational success. German commanders recognized by September 25th that the offensive had failed. Field Marshal Model ordered withdrawal of 5th Panzer Army as remaining armor to defensive positions protecting the approaches to the Saar industrial region. The failure at Arracourt consumed German armor reserves that might have been used more effectively in defensive operations during the autumn campaign. Abrams's 37th Tank Battalion specifically destroyed 24 confirmed German tanks during the battle while losing 3 Shermans. This 8-to-1 kill ratio resulted directly from disciplined HVAP employment and aggressive tactical leadership. Abrams received the Distinguished Service Cross for his actions at Arracourt, though official citations made no mention of ammunition effectiveness. Operational security requirements kept HVAP capabilities classified through 1945. The success at Arracourt created immediate demand for increased HVAP production. General Patton personally contacted Ordnance Department leadership in early October, requesting maximum possible allocation for 3rd Army. Similar requests arrived from 1st Army, 7th Army, and 9th Army as news of HV effectiveness spread through command channels. The Ordnance Department faced physical constraints. War Production Board allocated 200 tons of tungsten annually for ammunition production, enough for approximately 143,000 HVAP rounds. This supply had to serve all theaters: European, Mediterranean, Pacific. In practice, European theater received priority, but even maximum European allocation would provide only enough ammunition for 4-5 HVAP rounds per tank per month across all armies. Production scaling required expanding civilian contractor participation. The Ordnance Department contracted with additional tungsten carbide manufacturers, Fansteel Corporation, Kennametal Inc., and General Electric's Carbaloy Division. These companies produced cutting tools and industrial dies using tungsten carbide, so they possessed necessary equipment and expertise. Converting capacity to ammunition production required relatively minor tooling modifications. By December 1944, monthly HVAP production reached 28,000 rounds, nearly triple the initial October allocation. However, demand continued exceeding supply. The Battle of the Bulge, which began December 16th, consumed HVAP stocks rapidly as American forces engaged large numbers of German Panthers and Tiger tanks. Ordnance officers instituted strict distribution protocols. Tank destroyer battalions received priority allocation 10 HVAP rounds per gun. Tank battalions received 4 to 6 rounds per 76mm gun, depending on operational situation. Units in defensive positions or in sectors with light enemy armor contact received reduced allocations. Black market trading developed within American forces, though documentation is fragmentary due to the technically illegal nature of such exchanges. Tank crews would trade cigarettes, captured German equipment, or other valuable items for additional HVAP rounds. Some ordnance sergeants reportedly hoarded small quantities of tungsten ammunition for barter purposes. The tungsten supply crisis prompted investigation into alternative penetrator materials. Soviet liaison officers observed American HVAP ammunition in late 1944 when joint operations briefly occurred in Eastern Europe. Soviet armor forces already employed similar PCR ammunition in their guns. Soviet engineers studied American 76mm rounds and provided feedback through military channels. Documents indicate Soviet technical assessment praised American sabot design, while noting their own tungsten supplies came partially from Siberian mining operations inaccessible to Axis forces. By March 1945, cumulative AP production totaled approximately 347,000 rounds. Distribution prioritized European theater, where German armor remained a significant threat. Pacific theater received minimal allocation. Japanese armor was light and easily defeated by conventional ammunition. German forces launched their final major offensive in the West on December 16, 1944. Operation Wachte am Rhein committed nearly all remaining German armor reserves, approximately 1,400 tanks and assault guns including 450 Panthers and 45 Tigers to a surprise attack through the Ardennes forest. The offensive aimed to split Allied armies, capture Antwerp, and force a negotiated peace. American forces in the Ardennes, primarily First Army units, faced the heaviest German armor concentration since Normandy. Initial German advances achieved tactical surprise and local superiority, destroying several isolated American units. However, American forces held critical road junctions, notably Bastogne, disrupting German timetables. Tank crews engaging German armor during the Battle of the Bulge benefited from accumulated HVAP stocks. By mid-December, many tank battalions carried 8 to 12 HVAP rounds per 76mm gun, double the Arracourt allocation. This increased supply reflected higher production rates and recognition of HVAP's combat value. Combat reports from the Ardennes show American tank crews employed HVAP more liberally than in September. With larger allocations, commanders authorized HVAP use at longer ranges and in less certain tactical situations. This reduced the per-round effectiveness compared to Arracourt, but maintained overall kill ratio advantages. 7th Armored Division, defending St. Vith, engaged elements of 6th Panzer Army from December 17th through 21st. After-action reports document destroying 42 German tanks, including 28 Panthers, while losing 18 Shermans. HVAP expenditure totaled approximately 190 rounds, an average of 4.3 rounds per confirmed Panther kill. This effectiveness ratio, while lower than Arracourt's 2.93 average, still demonstrated significant improvement over conventional ammunition. 3rd Army's relief of Bastogne involved heavy armor combat. 4th Armored Division, the same unit that fought at Arracourt, led the attack north from Luxembourg. Combat Command Reserve engaged Panzer Lehr Division south of Bastogne on December 23rd. The engagement destroyed 16 Panthers and damaged 12 more, costing 4th Armored 8 Shermans. HVAP ammunition proved decisive in several close-range encounters, where Panthers attempted to ambush the American column. German commanders noted American ammunition improvements in intelligence assessments. A captured German document from January 1945, originating from OB West, Commander-in-Chief West Intelligence Staff, states, American 76mm guns demonstrate significantly increased armor penetration capability compared to summer 1944. Panther. Frontal armor no longer provides adequate protection at combat ranges. Recommend tactical doctrine modification, emphasizing long-range engagement and avoidance of close combat. Allied forces began Rhine crossing operations in March 1945. By this point, HVAP allocation had increased to approximately 15 rounds per tank, sufficient for extended operations without resupply concerns. German armored resistance had declined significantly due to fuel shortages, crew training deficiencies, and equipment losses during the winter campaign. First Army's crossing at Remagen on March 7th encountered limited armor opposition. Ninth Army's Operation Plunder, the set-piece Rhine crossing north of the Ruhr, involved over 1,200 tanks but encountered fewer than 50 German armored vehicles. The vast majority of German armor had been destroyed during the Ardennes offensive and subsequent defensive operations. The first M26 Pershing heavy tanks reached Europe in February 1945, nearly 2 years after development began. The Pershing mounted a 90mm M3 gun, capable of defeating any German armor at standard combat ranges. Its own Armor 100mm frontal plate provided protection against most German anti-tank weapons. Ordnance Department deployed approximately 310 Pershing tanks to European theater before Germany's surrender. These tanks equipped priority units. 9th Armored Division received the first allocation, followed by 3rd Armored Division and 2nd Armored Division. The limited numbers reflected production bottlenecks and shipping delays. The Pershing's arrival did not eliminate HVAP ammunition's importance. Most American armored forces continued operating M4 Shermans through war, and logistics could not support wholesale tank replacement, even if production permitted. Sherman crews remained dependent on HVAP ammunition for defeating heavy German armor. Combat performance of Pershing tanks demonstrated the value of superior firepower. At the Elsdorf engagement on February 25th, a single Pershing from 3rd Armored Division destroyed 2 Panthers and a Tiger, one at ranges between 900 and 1,200 meters. The 90mm gun's kinetic energy far exceeded what 76mm HVAP could deliver, even with tungsten penetrators. However, Pershings encountered reliability problems. Their complex powertrains and heavy weight, approximately 46 tons, stressed components designed for lighter vehicles. Transmission failures and final drive breakdowns occurred frequently during initial deployment. Sherman tanks, despite firepower limitations, maintained superior mechanical reliability, a crucial factor in sustained operations. Final accounting of AB ammunition production shows approximately 350,000 rounds manufactured between October 1943 and May 1945. Distribution prioritized European theater, where 94% of total production went. Pacific theater received minimal allocation since Japanese armor posed negligible threat to American tanks. Post-war analysis by the Ordnance Department credited HVAP ammunition with approximately 2,400 confirmed. German tank kills roughly 16% of total German armor losses on the Western Front. The study estimated HVAP prevented approximately 800 to 1,200 American tank losses by enabling frontal engagement of Panthers rather than requiring flanking maneuvers or withdrawal. Crew casualty analysis suggests HVAP ammunition prevented approximately 4,000 to 6,000 casualties among American tank crews. This estimate derives from comparison of casualty rates in units with adequate HVAP supply versus units with limited tungsten ammunition. The improved kill ratios and reduced need for risky flanking maneuvers directly translated to increased crew survival. HVAP ammunition remained in U.S. inventory after World War II. Stockpiles totaling approximately 180,000 rounds were maintained for potential use by occupation forces and National Guard units. When North Korean forces invaded South Korea in June 1950, American armor units deployed with VAP as standard anti-armor ammunition. Korean War tank combat occurred primarily during 1950–1951 before the conflict stabilized into static warfare. North Korean forces initially fielded Soviet-supplied T4 HVAP medium tanks mounting 85mm guns. These vehicles significantly outmatched the M24 Chaffee light tanks initially available to American forces. M4 A3 E8 Sherman tanks, essentially late production Shermans with improved suspension and 76mm guns, arrived in Korea in July 1950. These tanks carried HVAP ammunition from World War II stocks. Combat reports from the Pusan Perimeter and Incheon campaign show HVAP effectively defeated T4 HVAP armor at typical engagement ranges. However, Korean combat revealed HVAP limitations against newer armor metallurgy. Soviet T4 HVAP tanks produced after 1945 used improved armor steel with higher hardness than German Panthers. Some HVAP rounds shattered on impact rather than penetrating, particularly when striking at high obliquity angles. This performance degradation reflected the fundamental limitation of tungsten carbide. Extreme hardness makes the material brittle under certain impact conditions. The Ordnance Department responded by developing improved armor-piercing ammunition using better core designs and modified sabot configurations. The M331 APDS armor-piercing discarding sabot round, introduced in 1952, employed a longer, more slender tungsten penetrator with improved ballistic cap design. This round achieved approximately 1,100 meters per second muzzle velocity and demonstrated more consistent penetration against post-war armor steels. M26 Pershing tanks and M46 Patton tanks, improved Pershings with more reliable engines, formed the primary American armor force in Korea after late 1950. These tanks mounted 90mm guns firing improved HVAP rounds with performance exceeding wartime 76mm ammunition. Tank versus tank combat declined significantly after early 1951 as North Korean armor was largely destroyed and Chinese forces employed limited numbers of tanks. Tungsten supply remained constrained through the Korean War. The United States increased domestic tungsten mining during the late 1940s, but production remained insufficient for unlimited ammunition manufacture. Rationing continued, though less severe than World War II levels. This persistent scarcity drove research into alternative penetrator materials. The fundamental principles demonstrated by World War II VAP ammunition, small, dense, hard penetrators at high velocity, became the basis for all modern kinetic energy anti-armor projectiles. Post-war development focused on increasing penetrator length to diameter ratio and velocity while maintaining structural integrity during barrel launch. Research during the 1960s investigated depleted uranium as a penetrator material. Depleted uranium, U-238, offered density advantage over tungsten, 19.1 grams per cubic centimeter versus 15.6 for tungsten carbide. This density translated directly to superior penetration performance at equivalent velocities. Additionally, uranium exhibited self-sharpening characteristics upon impact. Uranium penetrators fractured in ways that maintained sharp tip geometry rather than mushrooming like steel penetrators. The United States Army adopted depleted uranium penetrators for the M735 APFSDS, armor-piercing fin-stabilized discarding sabot, round in 1978. This ammunition equipped the M60A1 tank as 105mm gun, achieving penetration performance exceeding contemporary tungsten designs. However, Concerns about depleted uranium toxicity and radiological contamination limited its acceptance among NATO allies. Several European nations continued developing tungsten alloy penetrators. The M1 Abrams tank, entering service in 1980, mounted a 105mm gun, firing M735 depleted uranium ammunition. When the tank was upgraded to the M1A1 variant in 1985, it received a 120mm smoothbore gun firing. M829 APFS DS ammunition, also using depleted uranium penetrators. The M829 round achieved approximately 1,650 meters per second muzzle velocity, delivering kinetic energy far exceeding anything possible with 76mm World War II guns. Modern APFS DS ammunition employs fin stabilization rather than rifle barrel spin. The penetrator itself is a long, thin rod, typically 500 to 600 millimeters, long with 20 to 25 millimeter diameter, wrapped in a multi-piece sabot that separates after barrel exit. Flight stabilization comes from small fins at the penetrator's base. This configuration maximizes penetrator length while maintaining ballistic stability, achieving penetration depths exceeding 600 millimeters of armor steel at 2,000 meters range. The design evolution from 1943 HVAP to modern, a PFSDS, demonstrates continuous refinement of the subcaliber penetrator concept. Each generation increased velocity, improved aerodynamics, optimized penetrator geometry, and employed better materials. The fundamental physics, concentrate kinetic energy through small, dense, hard projectile, remained constant. The civilian engineer who developed the original T4 HVAP concept remains largely anonymous in declassified records. His name appears in technical reports only as BRL research staff or similar designations reflecting wartime security protocols. Post-war documents reference Ballistic Research Laboratory Development Team without identifying individual contributors. Some records suggest the primary developer was Dr. James H. McMillan, a civilian engineer employed at Aberdeen Proving Ground from 1941 through 1963. However, this attribution remains uncertain due to incomplete documentation. Many wartime development projects involved multiple contributors whose individual roles became obscured in institutional memory. Major General Gladian Barnes received limited recognition for authorizing HVAP production over Ordnance Committee objections. His official biography notes responsibilities for ammunition development but does not specifically mention HVAP. Barnes retired from active duty in 1946 with the Distinguished Service Medal for his wartime contributions to ordnance development. Creighton Abrams achieved significant recognition for his tactical leadership, though not specifically for HVAP employment. He received the Distinguished Service Cross for actions at Arracourt, was promoted to general officer rank during the 1950s, commanded U.S. forces in Vietnam from 1968 to 1972, and served as Army Chief of Staff from 1972 until his death in 1974. The M1 Abrams tank, named in his honor, entered service 6 years after his death. Historical assessment of HVAP's impact has evolved. Early post-war studies, including the Army's official combat history series, devoted minimal attention to ammunition effectiveness. Analysis focused primarily on tactical maneuvers, strategic planning, and command decisions. Technical factors like ammunition performance received limited examination. Detailed analysis emerged during the 1980s when military historians gained access to previously classified ordnance records. Studies by R.P. Honeycutt, notably Sherman, A History of the American Medium Tank, provided comprehensive technical examination of ammunition development and combat effectiveness. These works established HVAP as a critical factor in American armor operations during 1944-1945. Modern historical consensus recognizes HVAP ammunition as a significant technical achievement that materially improved American combat effectiveness against German heavy armor. The development demonstrated that tactical problems could be addressed through technical innovation even when conventional solutions, heavier tanks, faced production and deployment delays. The broader lesson concerns institutional resistance to unconventional solutions. The Ordnance Committee's initial rejection of HVAP reflected reasonable concerns about tungsten scarcity and manufacturing challenges. However, their dismissal of positive test results demonstrated how bureaucratic inertia can obstruct beneficial innovations. Barnes's willingness to circumvent standard review processes proved crucial to fielding effective ammunition before war's end. The subcaliber penetrator concept pioneered in 1943. HVAP ammunition forms the foundation for all modern kinetic energy anti-armor munitions. Current tank guns from the United States, Russia, China, and European nations fire variations of the same basic design. Dense penetrator wrapped in lightweight sabot, achieving high velocity through reduced projectile mass. Contemporary examples include the M829A4 APFSDS round for the M1A2 Abrams, firing a depleted uranium penetrator at approximately 1,650 meters per second from a 120 mm smoothbore gun. The German 63 German Marks round employs a tungsten alloy penetrator with similar ballistic performance. Russian 3BM60 ammunition uses tungsten-depleted uranium composite penetrators launched at comparable velocities. These modern rounds achieve penetration performance far exceeding World War II capabilities. The M829A4 can defeat approximately 700 millimeters of rolled homogeneous armor steel at 2,000 meters range, roughly 5 times the capability of 1943. HVAP against much thicker, more sophisticated composite armor arrays. However, the fundamental physical principles remain identical. Penetration depends on kinetic energy, function of mass and velocity squared, delivered through small cross-section against armor target. Higher density materials concentrate more mass in smaller volume. Harder materials maintain structural integrity during penetration. Higher velocity increases kinetic energy delivery. These relationships, understood by ballistic engineers in 1943, continue governing modern ammunition design. The evolution reflects improved manufacturing capabilities rather than new physics. Modern penetrators employ advanced tungsten alloys with carefully controlled grain structure and sintering processes. Computer-controlled machining achieves dimensional tolerances measured in micrometers. Sabot designs optimize for clean separation at extreme velocities without inducing projectile instability. Gun tube metallurgy withstands higher pressures and sustained firing cycles. Beyond armor penetration, subcaliber projectile concepts influenced other military technologies. Anti-aircraft ammunition developed during the 1950s employed similar principles. Small, dense penetrators accelerated to extreme velocities for engaging fast-moving aircraft. The 20 mm APDS round fired by the M61 Vulcan cannon uses tungsten penetrators separated from aluminum sabots, achieving velocities exceeding 1,100 meters per second. Naval applications include armor-piercing projectiles for ship-mounted guns. The United States Navy's 5-inch 54 caliber gun fires subcaliber tungsten penetrators for engaging armored surface targets. These rounds achieve sufficient penetration to defeat warship armor at ranges exceeding 10,000 meters. Even small arms ammunition has adopted subcaliber concepts. Certain specialized rifle rounds employ tungsten or steel penetrators in polymer sabots, designed to defeat body armor at rifle combat ranges. While controversial for legal and humanitarian reasons, these rounds demonstrate the versatility of the basic subcaliber principle. The technical legacy of World War II HVAP development extends beyond military applications. Industrial cutting tools, mining equipment, and specialized manufacturing processes employ tungsten carbide components, optimized through research originally funded for ammunition development. Post-war declassification of wartime tungsten carbide research accelerated civilian industrial applications. The development and deployment of 76mm HVAP ammunition during 1943 to 1945 demonstrates how technical innovation can address tactical challenges when institutional and material constraints limit conventional solutions. The United States entered World War II with medium tanks adequate for defeating expected German armor. By 1943, German technical advances, specifically the Panther tank, rendered American tanks significantly outmatched. The conventional response, develop heavier tanks mounting more powerful guns, required extensive time for design, production, and deployment. The M26 Pershing, begun in 1942, did not reach Europe in meaningful numbers until March 1945. Alternative approaches were necessary to bridge this capability gap. HVAP ammunition provided that alternative through application of known ballistic principles. Reduce projectile mass to increase velocity. Use harder materials to improve penetration mechanics. Accept manufacturing challenges to field effective weapons quickly. The solution required no exotic technology, only willingness to challenge conventional assumptions about ammunition design and overcome bureaucratic resistance. The strategic impact, while difficult to quantify precisely, was substantial. American tank crews gained capability to engage German heavy armor frontally rather than requiring flanking maneuvers. This reduced casualty rates, increased tactical flexibility, and improved operational outcomes. The Battle of Arracourt demonstrates what properly employed HVAP could achieve. Kill ratios favoring American forces despite German technical superiority in tank design. Modern military forces face analogous challenges. Rapidly evolving threats, whether new armor technologies, improved defensive systems, or novel tactical doctrines, require responses faster than conventional procurement cycles allow. The HVAP experience suggests that technical innovation, pursued with sufficient determination and institutional flexibility, can bridge capability gaps pending long-term solutions. Contemporary relevance extends beyond armor penetration. The United States military currently confronts challenges in hypersonic weapons, directed energy systems, and electronic warfare domains, where adversaries may achieve temporary technical advantages. Responding effectively requires the same combination of technical creativity, bureaucratic agility, and willingness to challenge conventional wisdom that characterized HVAP development. The civilian engineer who designed HVAP working in a cramped laboratory, using rejected industrial materials, pursuing a concept multiple experts declared impossible, exemplifies innovation under constraint. His work saved thousands of lives and materially influenced World War II outcomes. That his name remains largely unknown reflects the nature of wartime technical development, where institutional credit often obscures individual contributions. Creighton Abrams' leadership at Arracourt demonstrates how tactical commanders must understand and exploit available capabilities. His decision to strictly ration HVAP ammunition, reserving tungsten rounds for high-probability engagements, maximized the limited resources' effectiveness. This disciplined employment proved as important as the ammunition's technical characteristics. The narrative of HVAP development thus encompasses multiple lessons. Technical innovation can overcome material constraints. Bureaucratic flexibility enables rapid deployment. Disciplined tactical employment maximizes limited resources. Institutional memory often fails to recognize key contributors. And fundamental physical principles remain constant even as technologies evolve. For viewers interested in detailed World War II history, this examination of HVAP ammunition development provides insights into how technical, institutional, and tactical factors interact to determine combat outcomes. The story extends beyond a single weapon system to illuminate broader patterns in military innovation and adaptation.